Good evening, everyone. I would like to first thank the organizers for giving me the opportunity to present my work, the recent work with my collaborators. The title Decompositions of Scherk-Type zero-mean curvature surfaces. So the work is firstly motivated by this paper or by physicist Randall Kamian. And the paper talks about the decomposing the height function of Scherk's first surface. And after this paper, there were many works in this direction, and we also get motivated, and there were many open questions, and we try to find some partial answers in some direction. Okay, so first of all, minimal surface appear everywhere. Naturally, it appears in many physical systems like soap films and bubbles, also in liquid crystals, molecular layers, interfaces in material sciences, and crystal growths. Especially for this talk, it's important to understand the Scherk surface, that these surfaces appear in symmetric liquid crystals. These were observed experimentally. And also one of the most simplest minimal surfaces, which has these twisted structures, also appears frequently in nature and in materials, which is helicoid. And so understanding the hidden symmetries of these minimal surfaces and their decomposition mechanism could reveal some new geometric ideas, and also can link the PDE theory with some experimental observations. Okay, so first I would like to talk about minimal surface. So height function. So what I mean by height function. So a surface in Euclidean space E3. If for a function f from R2 to from defined in some domain omega of R2 to R is called a height function, and it parameterizes by capital F, x, y, f of x, small f of xy, and it will be a zero-mean curvature. It will generate a zero-mean curvature surface if it satisfies the following partial differential equation, the well-known minimal surface equation given by the equation 0.1. One of the well-known examples of this surface is classical Scherk minimal surface, and this is the expression of this, and this is the well-known saddle-like figure for this Scherk minimal surface. Now, so the point is, you can see from the nonlinear PDE of 0.1 that it lacks the superposition principle. So that means what I'm trying to say is that if F1 and F2 are two solutions of that PDE, it is not necessary that the F1 plus F2, if you add these two solutions, it will again generate another solution of that of the minimal surface equation. But what physicist Randall Kamian showed in that paper was that that for Scherk's minimal surfaces, the height function of the Scherk's minimal surfaces can be decomposed into infinite sum of dilated helicoids. So the left-hand side will be the height function of Scherk's minimal surface, and the right-hand side it will be an infinite sum of dilated helicoids. So what these dilated helicoids are? So these are scaled version of helicoids, and these individual helicoid terms will not be minimal, but topologically they will be minimal. Topologically they will be minimal, but not geometrically. So what this shows that non-linearity of this partial differential equation restricts us for adding to solutions of the minimal surface equation. But if some surface has some hidden symmetry, then maybe we can find some special decompositions, just like what Randall Kamian showed in Scherk surfaces. So let's start with the Scherk's minimal surface. It was first found by Henrik Scherk at 1835. And this is the equation. This is the one-parameter family of Scherk's minimal surfaces, and presented by equation number 0.3. And this is a one-parameter family, and the parameter ranges from 0 to pi by 2. Now we can see that although if theta, the parameter, if it tends to 0, the height function phi will converge to the height function of the helicoid. You can see from the equation 0.4. Now, the most interesting part is that while dealing with this decomposition, there was a very interesting Euler-Ramanujan identity And using that identity, Kamian decomposed this height function. So this is the Euler-Ramanujan identity that this identity involves the tan inverse function. So tan hyperbolic, cot, and tan inverse. So all these functions are related by this equation 0.5. And using this identity, what Kamian does was to decompose that height function into dilated helicoids. So in the expression 0.6, we can see that the expression tan inverse of y minus nl divided by x cos theta by 2, this is the dilated helicoids. So this will not be minimal surface, but what we'll say is it will topologically locally preserves the topology of a helicoid. Now, so what are the observations and what are the open questions one can ask from this? That this Scherk's minimal surface can be expressed as an infinite superposition of these dilated helicoids. And next, that from the expression you can see that only in the direction of x, if we have the dilation, then the right-hand side expression, the summation, will lead to a minimal surface in the left-hand side. That is the Scherk's minimal surface. Now the question is that due to this some hidden symmetry, this decomposition is possible for this Scherk's minimal surface, but whether such symmetries also exist for other minimal surfaces or not, and that was the open question. And also there is another question that there are also zero mean curvature equation in Lorentz-Minkowski 3 space, and those PDEs are actually related to the minimal surface equation or minimal surface PDE via weak rotation. So after weak rotation, is it possible that the symmetries are retained? If it is so, then how we can decompose them? So that is the analogous decompositions for these solutions. For such solution are again possible or not in after weak rotation. So in this direction, first of all, we have to talk about this weak rotation, how this weak rotation and maximal surfaces are linked. So maximal surfaces are space-like zero mean curvature surfaces in Lorentz-Minkowski space. So a weak rotation is actually analytically continues the real coordinate to an imaginary value, like x replaced by ix. I is the imaginary unit. So now in the Lorentz-Minkowski space, if the coordinates we change from, if you change the coordinates x to ix and y to iy, then any minimal surface equation, any solution to the minimal surface equation, if we replace, if we do this weak rotation, then the solution we arrive will be the function will arrive. We'll solve the equation 0.7, which is the maximal surface equation. For example, from classical Scherk's minimal surface, if we do this weak rotation, then obviously we get a Scherk's from Scherk's minimal surface, we'll get a maximal surface presented by G of xy. Now, similarly, what is the relation between weak rotation and Born infield solitons? So Born infield soliton was, so similarly, again, if we weak rotate the variable y to iy and redefine the coordinates from xyz to yzx, then one can map a minimal surface into the solution of a Born infield equation. So the Born infield equation here is represented here at by 0.8, and this is the zero mean curvature equation over the time-like yz plane in the Lorentz-Minkowski space. And the same classical Scherk's minimal surface, when we perform this weak rotation and the above process mentioned, then we will get a Born infield soliton. That is the solutions of the equation 0.8. Now, it is expected that after this weak rotation, the symmetries inside the Scherk's minimal surfaces are retained in these solutions also. So now what is the difficulty after performing this weak rotation? So in many cases, what happens that after weak rotation, we do not get real valued solution. Rather, we get complex valued solutions. For example, that if we perform weak rotation in the helicoid, in this expression of tan inverse of y by x, then we get weak rotated helicoid, and this is a complex valued Born infield soliton. Now the thing is, what the problem is that these complex valued solutions are not are problematic for real valued height functions. So they do not have any geometric significance. Now to deal with this problem, there was this paper by Shintaro Akamine and Rahul Singh that deals with this problem and also gives that under certain symmetry conditions which satisfied by the function f, we can, after weak rotation, the real solutions are retained. For example, this from this theorem, one can see that in if we start with fxy, which is even or respectively odd with respect to both the variables x and y, then after performing the weak rotation, the solution will get, obviously, it will be a maximal surface, solve the maximal surface equation, as well as it will also be a real solution to the maximal surface equation. And similarly, if it is, if from this theorem we can see that if it is even with respect to the y variable, then after performing the weak rotation, it also satisfies the it also retains the real solutions. From these two theorems, it is clear. Now, so now if we perform these weak rotations, and fortunately, our Scherk's minimal surface, the phi xy theta, this function actually in both coordinates x and y, they are odd. So, and therefore it satisfies all the conditions mentioned in the theorem, previously mentioned theorem. So therefore, after performing weak rotation, we get the Scherk's maximal surface represented by the equation 0.9. And in this expression, we can also see that if we take here also the limit as theta tends to 0, then the limit converges to again helicoid. Now, what we found was that similar to the Scherk's family of minimal surfaces, this family also allows similar decomposition due to the symmetry is unchanged, and this is the new family psi xy theta. It will satisfy this decomposition presented by equation 0.10. Now, similarly, we have this one parameter family of solutions to the Born-Field equation, also performed by weak rotating the variables from y and z. And after that, we'll get this Scherk-type Born-Field solutions derived from the Scherk's minimal surface. So given by the equation 0.11. And we'll call this solution Scherk-type Born-Field solutions. And here also, from this expression given at 0.11, the limit of this function also converges to the hyperbolic helicoid, the tan hyperbolic inverse of z by y. Now, similar to that, here also we are able to decompose this function also into the dilated complex helicoids. And so the height function of Scherk-type Born-Field solutions can be decomposed as an infinite superposition of dilated hyperbolic helicoids as presented in equation 0.12. So here one fact we have to understand, the left-hand side of the equation 0.12 is real, although the right-hand side is actually complex valued. So what are the observations from here? So in Randall-Kamian showed that the Scherk's minimal surfaces are infinite superposition of the limiting helicoids as theta tends to 0, as shown in the equation 0.4. Similarly, here also we see that the families psi and chi also decompose into superpositions of dilated versions of their respective limits as theta tends to 0. Now, from the expression 0.12, we see that I just mentioned that the left-hand side is real value, while the right-hand side involves the complex functions. So that if we take the imaginary sum, so that sum will adds up to 0, and therefore we get the following identity involving the Born-Field solution, and this is a completely real identity. One can see. Now we'll talk about the finite decompositions. Kamian also found some finite decompositions of Scherk's surfaces of up to itself. Now, in this case, we can and for that we can use this summation. We can break this summation into finitely many infinite sums. And so from equation 0.13 and 0.14 shows this infinite how we can break these decompositions. And so this after this decomposition and using these two equations, one can also find the finite decompositions of these surfaces up to themselves. So you can see from the expressions that psi, phi, and chi, all of them, that is the Scherk's minimal surfaces, maximal surfaces, and the Born infield solitons, all of them are related to each other by these expressions. And we have the following, infinite decompositions. Now we'll talk about some more observations in weakly untrapped and star surfaces in the four-dimensional Lorentz-Minkowski space. So in E14, any space-like 4-dimension 2 surface admits two independent future-pointing light-like normals. And we have this is the mean curvature vectors. And after Steno-Wheeler's classification, we know that a space-like zero mean curvature surface in this space will be called the maximal surface. It will be weakly untrapped if we multiply K1 and K2, it will be non-positive, and it will be star surface if K1, K2 is non-negative. So now what we will do is actually if we take any solutions of the maximal surface equation 0.1, then and we immerse that using the equations 1, 2, and 3 in the example immersions, then it will be ultimately you can see that they will be weakly untrapped. And star surface from F it will be weakly untrapped. Capital G will induce a star surface, and capital H will induce a weakly untrapped surface. So the key consequence is, so if we put that, so we have the dilated zero mean curvature surfaces in the Euclidean and in the Lorentz-Minkowski settings. Now, if we immerse those surfaces using this capital F, G, and H, then we will get weakly untrapped surfaces, and from F and H, and from capital G, we'll get the star surface. And from this, we can interpret our infinite decomposition or the finite decomposition results as that the Scherk's minimal surfaces in E3 can be seen as an infinite sum of weakly untrapped surfaces in E14. So I have to mention that this summation is not the geometric summation as like we are not adding the parameter additions, but it is in an analytic sense that we are adding the functional values. Similarly, Scherk's maximal surface in E13 can be seen as an infinite sum of star surfaces in E14, and the Scherk-Type born infield solitons in E13 can be seen as an infinite sum of weakly untrapped surfaces in E14. And from the finite decomposition theorem, we can see that if we keep these suitable immersions, then the Scherk-type surfaces into E14 yield their space-like locus as finite sums of weakly untrapped and star surfaces. So the summary is that we have extended the Camion's decomposition results from minimal surfaces to maximal surfaces and born infield solitons via weak rotations, and then express this family of phi, psi, and chi. These are the Scherk's minimal surfaces, maximal surfaces, and also the born infield solitons obtained after weak rotations into infinite sum of dilated versions of one another. And lastly, as an application of this decomposition, we express this space-like maximal surfaces in U14 as finite and infinite sums of weakly untrapped and star surfaces. So what are the questions? The question still remains is that we still need to characterize all such families of ZMC surfaces which admits this similar kind of decompositions, and what type of analytic properties are there in a height function which admits such decompositions. Thank you.
That wonderful talk. Are there questions from the audience? Oh, yes.
So I have a question regarding the minimal surface equation. So when you are changing the variable from x to ix, the coordinate,
Yes.
So you are using the complex structure and the metric over the complex structure?
No. Actually, if you just put the equations, if you put the solution just on the partial differential equation and solve that, you will get that the real part, the partial differential equation, both of the parts, the real and imaginary part will become 0. So it's you just substitute the values in the partial differential equation itself.
Then I have to.
Yes, you have to in the solution. So suppose you start with a if fxy is a solution of the minimal surface equation, then construct a new function g of xy. Suppose it is f of ix comma iy, and now it will satisfy this new function will satisfy the maximal surface equation.
Subham, I have a question.
Additional question.
I'm online. Yeah. Can I ask a question, Charles?
I asked my naive question first. Okay.
Hello?
So
Charles, I have a
I
question
think maybe
from online.
you mentioned it, I just didn't quite catch it. So all these infinite sums that you have, I mean, it's actually, they converge absolutely then, so that it's...
No, these do not converge absolutely. This converges the symmetric partial sums actually.
I see. Okay. So that's what you mean by
Yes.
sums
So,
in quotation.
yes.
Why they have to take symmetric sums.
The symmetric partial sums.
I see. Okay. And then, okay, I mean, is there a way to visualize this, or is this all, kind of, because for your Scherk, you have your doubly periodic surface, and then you have all these helicoids that are clearly not doubly periodic, but somehow when you add it, you get all these.
So when Camion was, because experimentally you can see these things, okay. But there was no theoretical expression. So Camion used this expression for this Ramanujan's identity. So fortunately for this particular surface, there is this identity.
Okay.
And using this identity, he was able to decompose this surface. But experimentally, it can be seen actually.
So could you show me the formula again?
Hello? Sorry.
Sorry, Rukmini, why don't you
No. Please, Charles, go on. Please.
I'm wondering, so how does the shift look like? So could you show me this formula again that you have?
Which formula?
If you can show the picture of a Scherk surface, it's very clear how the helicoids are present. Yes.
So from this
from
picture,
here, you can see the helicoids present. Can you see?
Yeah, let's see. No, I'm not as sharp as you. Could you? Yeah.
So there are these along. It's like this. Sorry, I am no Subham. If you want, you please continue. Sorry.
No, madam, you can.
See, in each of these, there's a twisting you can see right along those ribs.
So I'm looking at
those are the helicoids. You have put them in an array, and you just sum it. The height functions just sum, but it's like, those in crystallography, it comes as screw dislocations. Screw dislocations, you have a lot of screw dislocations in liquid crystals. They look like helicoids. Okay, maybe next time when I come there, I will show you.
Yeah, I see.
Sorry.
So it's
yes.
not just a naive, vertical shift. I mean, that there's actually some...
Yes.
I mean, I think in your expression, it's in the argument of arctan, right? So it's not...
Yes.
And Camion mentioned it as a topological defect.
Yeah, so it's a topological defect, screw dislocation. Subham, I wanted to ask you, Soundarajan, Kohinoor and myself also got those decompositions. You have seen those papers, right?
Yes, ma'am.
So what is the difference between yours and ours?
Yes, ma'am. Actually, in your paper, it was there was more general result that you said about that any minimal surface equation, the height function, you can have finite decompositions using a particular, but the identity you have used is actually little different from what Camion has used.
No, I mean, okay, we can discuss this later, but we have also used Camion sort of arguments for, okay, anyhow, later on I can discuss. But if you are allowing scaling and translations, then actually it can be done for any minimal surface height function.
Yes, ma'am.
If you are allowing scaling and translation, the decomposed surfaces are not minimal actually, but scaled and this thing. So, but
Ma'am,
anyhow, we can talk about that later.
another one was that while was doing after the weak rotation, there was a challenge that the height functions becoming complex or imaginary. So in that case, the paper with Rahul sir and Shintaro Akamine, they sort it out that if this if you start with a function f which have this odd and even symmetries on the real variables, then you will have after weak rotation you can also have real solutions. So that is one other thing.
Okay. So, but I thought the ones you got here, I thought some of them we have already got, but anyway, never mind. Later on we can discuss that.
Okay, ma'am.
Okay.
Are there additional questions from the audience? Okay.
Yes, he is a physicist. Yes. Yeah, so while doing, he was talking, he was mainly concerned about liquid crystals. So in liquid crystals, these sharp surfaces appear as grain boundaries. So I don't understand that what that thing is, but in that context, he was interested about these sharp surfaces, and then he later found that this decomposition, we can found these decompositions.